Breault Research Organization is pleased to announce an optimization feature in its award-winning Apex Optical Engineering Design and Analysis software program. Optimization is a term used to describe the automated design of a system to find the best possible compromise between often conflicting performance requirements. Optimization is the automated adjustment of user-specified optical system parameters to improve your system's performance through a specified figure of merit based upon one or several objective functions. The optimization feature in Apex is workflow-driven, taking you through the process of setting up a study via the Optimization Study panel. Setting up an optimization study in Apex involves these essential activities: defining variables that can modify the specified geometry, setting any desired constraints, which create direct or indirect relationships among the design variables, and possibly the merit function used to limit or restrict the variable range, defining goals, which are some type of performance target you wish to achieve, and then selecting the surface measurement to which a goal is applied, running the automated optimization process, and then viewing the results on the Active Study tab. Now let's examine how we create an optimization study in Apex. First, you must have an optical system which can actually trace rays. Then click on the Design button and the Optimize tab in order to launch an optimization study. Now, Apex design variables can be created from driving dimensions, distance mates, spline tangent radial directions, or spline tangent weightings. In this particular example, we're going to be optimizing an elliptical reflector and a source placed close to its focus by changing the position of the source with respect to the reflector, the radius of curvature, and the conic constant of the actual elliptical surface. The interesting thing about this particular example, however, is the variables that we are defining to control the behavior of the actual curve are defined as simple line segments outside of the curve itself. However, they very conveniently reference equations which describe the actual geometry of the surface or the elliptical surface in this particular case. In order to add a design variable, click the Add Design Variable button. You can then find within your sketch that variable you'd like to add, highlight it, and click the checkbox, and that variable will appear in the Design Variable table. In the Design Variable table, you can rename the variable, and you can also set the minimum and maximum values of that particular variable. If you check the delta box, you will get a value which is on either side of the initial starting value as a minimum and maximum value. The tolerance in this particular case is a computational and not true manufacturing tolerance of the variable. Variables are changed by various amounts during optimization in order to find the best solution. The optimization algorithm will limit the amount of variable change to the tolerance amount when an optimization step or an estimate of the optimum attempts to change that variable by less than the specified tolerance value. You can additionally add notes in this field to give further information about the description of the variable that's used in the optimization. In this particular example, we have as variables the location of a source in the reflector, the radius of curvature of the elliptical shape, and the conic constant of the elliptical shape. The next step of the optimization process is actually optional, and this allows you to add constraints. Constraints can be applied only by using existing dimension sensors. A constraint, for example, could be the actual size of the reflector in this case, or its clear aperture. However, for the purposes of this demonstration, we are not going to add any constraints to our optical system. The next part of the Apex optimization workflow is to define a goal. Optimization goals are created in steps. In order to add a goal, you must first identify a target on which you want to place the goal. You then press the Add Goal button. That particular object is indicated in the measurement type box. You can choose from 4 different types of measurements: power, intensity, irradiance, or radiance. In this particular case, we're going to be optimizing or maximizing the amount of power on this particular detector plane. After clicking OK, you're presented with the goal geometry screen. In this case, you can enter goals either as points, lines, regions, polygons, circles, or ellipses. This can be demonstrated in the following example. Here's a region created with a point, which is added to the goals, and then a region created in the form of a polygon, which is then added to the goals. These goals can be shown together. However, they must be of the same measurement type. That is, they must be of a power, irradiance, intensity, or radiance. In our particular example, we're going to designate a circle with the center and a radius with the center located at 0, 0, and a radius equal to the radius of the detector. You also have the ability to average the data if necessary. However, in this case, we are not calculating an intensity, irradiance, or radiance calculation, only the amount of power on the detector plane. And you can also set the window properties in which one of those types of calculations, such as irradiance, intensity, or radiance, would be performed. You then press the Add to the Goals button and close the screen, and your goal is automatically added to the goal table. Apex also allows you to add or create composite goals of the goals and measurement types that you've specified. For example, we could create a composite goal composed of the point and the polygon, which is now shown as a composite goal in the table. However, for this example, we do not need these goals, so I'm going to delete them from the example. Apex allows you to control the figure of merit depending upon the values that you enter in for the target weight, the minimum and maximum values. If you enter a target value, you get the traditional center-seeking solution. For maximizing a value, if you right mouse click and choose maximizing a goal, Apex will attempt to maximize that particular parameter on the target that is specified. If you enter minimum and maximum values, you will force an edge-avoiding solution and configuration of the merit function. The minimum and maximum values are the edges to avoid during optimization. After you've configured your variables, you've added any constraints, and you've added your goals, you are now ready to set the optimization options. In this case, you have the ability to limit the number of trial solutions, use an absolute acceptance limit, a relative acceptance limit, or an acceptable noise limit. In this particular example, we will use an acceptable noise limit in addition to a limit on the number of trial solutions. The acceptable noise limit will be applied on 5 consecutively preceding trial solutions. When you have set your optimization options for exit criteria, you are then ready to hit the Run button and start the optimization. You will see a series of dialog boxes which appear on your screen, which are informing you of the optimization progress. You will see the number of trial solutions and the individual evaluations within those trial solutions as Apex attempts to find an optimum solution for your particular system geometry. Depending upon the number of rays that you have traced and the complexity of your system, this optimization may require some amount of time. When Apex is finished with its optimization, you will note on the optimization progress screen that the task is indicated as being done. You can close the screen down or use it to evaluate where your best solutions are for the optimization. When you are ready to view results, press the Results View Radio button, and you will see your trial solutions listed, along with the various variable parameters and the figure of merit. At the top, highlighted in green, is the optimal solution. And if you click on that, Apex will automatically set your geometry to that optimal solution. We can now examine how well Apex's optimization performed by doing a ray trace on the system geometry. As you can see, Apex has very nicely optimized the optical system by moving the source and changing the radius of curvature and the conic constants of this reflector system in order to produce an optical system which has been optimized to maximize the amount of power on the detector. So that was just one example of optimization in Apex 2011. Here is another example of a TIR reflector. The TIR reflector is composed of both reflecting and refracting surface elements. Apex's optimization allows you to control spline tangent radial directions and weightings, which in turn control the shape of curves, and changing these parameters allows you to change the curve shapes in order to meet your optimization goals. In this particular example of the TIR-optic, we start with an initial ray trace and an initial analysis, which shows that the output distribution of intensity from the TIR-optic is basically a Gaussian shape. After running the system through Apex's optimization, we end up with an optical system which is optimized such that the output intensity is very nearly uniform. Let's compare this to the original system. Here's the original system and its nearly Gaussian intensity distribution, and here's the optimized system with its nearly uniform intensity distribution. Apex, the natural nexus of virtual prototyping for optical system product development in a concurrent engineering environment, now has a powerful optimization capability. Optical design based upon automated optimization, a term used to describe the automated design of a system to find the best possible compromise between often conflicting performance requirements, has changed radically since its first incorporation in traditional lens design codes nearly 50 years ago. An optical system cannot be designed by simply drawing optical component shapes in a CAD environment. The spatial and angular interaction between light and optical shapes and optical materials must be mathematically accounted for after it interacts with the optical components. Apex now provides these tools in an automated sense with its new graphically driven optimization feature. Apex's intuitive graphical interface now includes a powerful optimization capability that allows users to interact light with optical and mechanical geometry. The spatial world of CAD is linked to the mathematical world of optimization through Apex.